Good morning. Alright, this video is just a quick video to help people maybe with a critical challenge or to understand orbital velocity versus launch velocity. Alright, so we have, let's say, Earth or some planet, and then I put a little dot here to be the very center of the planet. Maybe a satellite is orbiting around the planet in a circle. And then we have this point way out here, which is an infinity distance away, or enough far away so that's no longer in the gravity field of the Earth or this planet. But we'll say it's an infinity distance away. So the one thing to note is infinity distance away, your potential energy is going to be 0. Okay? That's how it's denoted. Your potential energy is 0 at infinity distance away. And as you get closer and closer to the center of your planet, that's when potential energy goes to negative infinity. So it goes more and more negative until you reach the center. Okay? And potential energy is 0 there. Alright, so let's talk about orbital velocity. So we have orbital velocity. What does that mean? Orbital velocity means how fast you're going tangentially as you go around your planet in, say, this orbit here, whatever it is. So it's how fast you're going around in that orbit. Okay? The interesting thing about orbits is the faster you go, the actually further out you go. The slower you go, the further in you go. So each orbit has its specific orbital velocity. And how you find out what its specific orbital velocity is you use your equation Fg equals Fc. Because it depends on the gravity. That tells you how fast you go tangentially around your Earth. Okay? So if Fg equals Fc, because the force of gravity is what's keeping it going around in a circle. Okay? It's the force that keeps it in. So Fg is this universal constant times your mass of your satellite times mass of your planet over the radius squared. No, not the radius squared, but the distance from the center of the Earth to your satellite. Okay, so you might have to find the distance from the center of the Earth to the surface of the Earth and the distance of the surface of the Earth to your satellite. Okay, and then the other one here is Fc. So Fc we know is mv squared over r. Okay, so we have these two equations, and I'm not going to do big R, I'm going to do the same R as that, because we know that those two things are the same. The radius of the circle is this, from the center of the Earth to your satellite. And then this is the mass of your satellite here, so that's going to be the same as this here. Turn off this light. Alright, so overall we have this equation. We can see that m's cancel out, and then you're left with an r and an r cancel out. So we have a g mp over r equals v squared. Okay, so your orbital speed is just this, so we can square root. So overall our square root of g, our mass of our planet, and our r. Okay, so that's orbital velocity. It always depends on the mass of whatever planet it is and how far away you are from it. Okay, and now let's move on to launch velocity. The second one, launch velocity. There's two types of launch velocities. There's one where you're going from one spot to another spot. So say from the surface of the Earth to your satellite orbit spot. And then there's another one called, it's done the same way, escape velocity. It's your velocity you need to go from the surface all the way to this infinity spot where potential energy is 0. Okay, so how you do these ones is you always go total energy in one spot is equal to total energy in a second spot, because conservation of energy says the energy in two spots have to be the same. So here we can always go potential energy in one spot plus the kinetic energy in that first spot is equal to potential energy in that second spot plus kinetic energy in that second spot. That's how you always do either of these ones. Sometimes your first spot, say, will be the surface of the Earth, and your second spot is the satellite spot. So it's this velocity you need to get from here to here. It has nothing to do with orbital speed velocity. Alright, and then you could also make your second spot this infinity spot if you wanted. Alright, so we have this. Potential energy for space always uses this equation. Negative G M1, your mass of your planet, over R of your first spot. Okay? And the kinetic energy is the same as it normally is. And then your potential energy in your second spot is either going to be this, but this time in your second spot, so your R is going to be different than over here. And that's a 1 as well. And then your kinetic energy generally is always 0 in your second spot, because you just want to get to that second spot and you don't want any speed at that second spot. So you normally have this equation, and then you can usually get rid of any of your satellite masses because they're in every equation. And then you can fill in all your values and solve for your speed. And that tells you how fast you're going to get to your second spot. Okay? If it's escape velocity, you'll notice that your potential energy in the second spot is just going to be 0. So if we look at the picture again, potential energy in that infinity spot is 0. Okay? So escape velocity is actually a bit nicer to work with than launch velocity. Thanks.